So our first example using the rational roots theorem will be this example here. Okay, we're going to solve the polynomial equation x cubed minus 6x squared plus 11x minus 6 equals to 0. Okay. And so here I have written our rational roots theorem, which we're going to use here to try to solve this equation. Again, the rational roots theorem doesn't guarantee us a solution, but it helps us to reduce the number of possible values that we want to test to a more manageable list. So if this equation a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1 x plus a naught equals 0, then if there are rational solutions, they are of the form p over q, where p is a factor of the constant term a naught, and q is a factor of the a sub n, the leading coefficient. Okay, so let's examine that in the context of this polynomial. Okay, we can see that this is the leading term because it has the greatest power, and we can see that this is the constant term. Okay, so in other words, we know that our an x to the n will be, to use the notation from the rational roots theorem, it'll be here x cubed, or as we've mentioned before, 1x cubed. I want you to remember this is a shorthand for this. Okay, so we can see right away that our leading coefficient a sub n is 1. Okay, moreover, this right here, the negative 6, is going to be our constant term. Our a0 is negative 6. Okay, so now we know what our leading coefficient is and what our constant term is. Okay, I want to make that very clear. So now we want to make a list of our possible p's. Okay, oops, or not our possible p's. Our p's are going to be our p's, not to be confused with green peas, which are the delicious like vegetable that you eat, but the numerator of the possible roots. So our p's are going to be, in this case, the factors of the constant term. What's our constant term? Negative 6. Okay, so here let's say factors of constant term. Okay, that's what it is, right? And so we can write that as, so what are the factors of 6? 1, because 1 times 6. So I'm going to put plus minus 1. 2, because 2 times 3 is 6, right? So I'm going to put plus minus 2. 3, why? Because 3 times 2 is 6. So plus minus 3. And then finally 6, because 6 times 1 is 6. Okay? So these are my possible factors of my constant term a0. Now, what are my factors? My q's are going to be my factors of the leading coefficient. Okay? Right? What are the factors of 1? Plus or minus 1. Why? 1 times 1 is 1, or negative 1 times negative 1 is 1. Okay? And we know that that's basically it. Okay? Okay. So now here is the main thrust of this theorem. We know now our factors of our constant term. We know now our factors of our leading coefficient. We didn't check it, but you can see here that the polynomial does have integer coefficients, so the rational roots theorem can apply, and we say that the possible rational roots, okay, in other words, the possible solutions, if they exist, if there's rational solutions, okay, are going to be like this. I'm going to make all the possibilities of a p divided by a q. So what is, I'm going to make it here, what is, let's first take all of these to be positive, and I'm going to divide them by positive 1. So 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. Now I'm going to take the negative ones from here, and I'm going to divide them by the positive one. So what's negative 1 divided by 1? Negative 1. What's negative 2 divided by 1? Negative 2. What's negative 3 divided by 1? Negative 3. What's negative 6 divided by 1? Negative 6. Okay? And then we can take the positive here, divide them by the negative 1, and we would duplicate this column, this row. And if we took the negatives from here, from the p's, and we took the negatives from the q's, we would duplicate the first row, the 1, 2, 3, 6. And so, in other words, after we have formed all the possible fractions, p divided by q, for each p in our list of the factors of the constant term, and for each q in the factors of the leading coefficient, we end up with a list of the possible rational roots. So look at this. We started with a polynomial where we have no formula to solve it explicitly, as we did in the case of a quadratic. We would have had to try infinitely many possible numbers to try to solve this equation, okay? But thanks to the rational roots theorem, we now can try 8 numbers, and if the polynomial has a rational root, we will find a rational root. And if it only has rational roots, we will find them all because they'll all be in this list, okay? Okay. So now let us actually do that. Let's actually test to see which one of these is a root, okay? So we can even make a table, okay? Okay, so this will be the x that I'm going to test, and this will be the expression. X cubed minus 6x squared plus 11x minus 6. I want to evaluate this expression at the value. Like, let's say if I take x equals 1. Okay, let me make a quick observation here, which is extremely important. If we want to solve this equation, since it's a cubic, if we just find one root, then we can use the factor theorem to divide out by the corresponding factor, and then we can use the quadratic formula or factoring or whatever other technique we want, okay? So we don't have to test out all of these, okay? But let's try one for an example. Let's evaluate it explicitly, okay? 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. What is 1 cubed? 1 cubed is 1 times 1 times 1. What's that? 1. So I can see that this is going to be equal to 1. What is 1 times 1? 1 times 6, 6. So it stays minus 6. 1 times 11 is 11. So I stay plus 11. And then I bring my minus 6 down. What does this simplify? 1 minus 6 is negative 5. Then I bring down the rest of this. Plus 11 minus 6. What is negative 5 plus 11? That's positive 6, right? Then I bring my negative 6 down. And what is 6 minus 6? 0. Oh my God, look what just happened. We tested with we tested with the possible value 1, and we got that this expression simplified to 0. Okay? So let me not write this. So root, yes, okay. Okay. Maybe I shouldn't have put this here. Maybe I should have put that out to the side. Okay? But that's what I'm basically going to be doing, right? So I tested it, I evaluated it, and I got that it gave us 0. Okay? So now we know that 1 is a root, and hence x minus 1 is a factor of this polynomial. Okay? Because that's the factor theorem. And so let me see here. But we could try the other terms, okay? And let me write that in as part of the table actually before I continue, because that's also very important information that I don't want you guys to lose sight of, okay? So plus x minus 6, is it a root? In other words, is it a solution of this equation, right? And if so, what is the associated factor? Right? So in this case, it was a root, and the associated factor in this case would be x minus 1, right? Okay. Okay. Let me get a different pen here. Let's now try -1, okay? How would -1 evaluate? Well, it would be -1 cubed minus 6 times -1 plus, -1 squared here, plus 11 times -1 minus 6. What's -1 cubed? -1 would be -1 times -1, which is +1, times -1 again gives me -1. So this would become -1. Now I have -1 squared. -1 times -1 is +1. So I have -6 times +1, which stays as a -6. Okay? Now I have 11 times -1. That becomes -11. I'm adding a -11. What does that become? That becomes -11. Okay? And then I bring down my -6. Okay? Okay. Okay. So now here, what is -1 minus 6? This is -7. And then I bring down my -11 minus 6. What is -7 minus 11? This is -18. And then I bring down my -6. Notice how I'm doing them 2 at a time, working my way until I get the whole expression simplified. And then -18 minus 6 is -24. Okay? Is this a root? Is this a solution of this equation? No. Is there an associated factor? No. Right? So now, and what you can see here is that we're going down the list of possible roots. Now again, strictly speaking, once we find one root, we can divide this polynomial by the factor, and then it can help us to evaluate, it can help us to basically solve this equation. In that case, right, if we were to divide out by this factor, right, we would end up with a quadratic, and then we can just apply the quadratic formula or factoring, whatever technique we want to use. But let's just try these out a little bit more. Let's just try a couple more to see how we're doing this, right? So we want to evaluate this polynomial at the value 2. So we plug that in. What is 2 cubed minus 6 times 2 squared plus 11 times 2 minus 6? Okay? I'm evaluating the polynomial expression at 2 to see if it will equal 0. What's 2 cubed? 2 times 2 is 4, times 2 again is 8. Okay? 2 times 2 is 4, times 6 is 24, so this becomes minus 24. What's 11 times 2? 22. So this becomes plus 22. Then I bring down my minus 6. Okay? What is 8 minus 24? That's minus 16. Then I bring down the rest of this calculation. By the way, one of the things I want you to observe here is how I'm extremely careful about how I perform these calculations. What is negative 16 plus 22? That's positive 6. Okay? And so I get 6 minus the 6, that's 0. So this one is a root, okay? And the associated factor would be x minus 2, right? Because if you have a polynomial f of x and r is a value that makes f of r equal to 0, then x minus r is a factor. Okay, let me write that out for us. So let me just again remind you of that result. The factor theorem says that f of x is a polynomial and f of r is equal to 0 for some r, some real number r. Then x minus r is a factor of the polynomial, right? Okay. Okay. Now you can see these possible rational roots have given us already 2 roots of this polynomial. And they're rational because in this case they're whole numbers. But of course they could have been, so rational numbers, as you know, are all the numbers that can be represented as a fraction of integers. Okay, so the rational roots could be like 1/2, 3/2, etc. In this case, they're even nicer. They turn out to actually be integers. Now, I also want to point out something else. -1 was not a root of this. Was not a root and not a solution of this equation. So I want you to realize why I wrote this as the possible rational roots. The rational roots theorem does not tell us that that all the members of this list will be roots. It tells us that some might be. Okay? Okay. That some or none might be. This polynomial may have no rational roots whatsoever. And so in that case, the list might have some possibles, but none of them would work. In this case, we see that this list of possible roots has already yielded two roots. Okay? We've done that through explicit calculation. So now let's proceed. Let's go down the list a little more. Okay? Let's try 3 as an example. Okay? Or should we try -2? Let's try -2. Let's not get ahead of ourselves. So it would be -2 cubed minus 6 times -2 squared plus 11 times -2 minus 6. Let's evaluate this expression. What is -2 cubed? That's -2 times -2 times -2, right? -2 times -2 is +4. Times -2 gives us -8. Okay? Look at this here. What is -2 times -2? That's +4. Times -6 is -24. What is -2 times 11? That's going to be -22. I'm going to add a -22. That's going to give me -22, right? And then finally I bring down my -6. Okay? What is -8 minus 24? That's -32. Okay? So that represents these two, so I bring down the rest of this. -22 minus 6. Now, what is -32 minus 22? That's going to be -54, right? -54. Then I bring my -6 down like this. And then I ask, what is -54 minus 6? And that's -60. Okay? So is -2 a solution of this equation? Is it a root of the polynomial? No, it is not. Okay? And so this, let's say, not applicable. Okay? Because you need to have a solution of this equation for there to be a factor of the polynomial. Okay? Okay. And so now let's try x equals 3. Okay? Okay. So let's evaluate this expression. What is 3 cubed minus 6 times 3 squared plus 11 times 3 minus 6? First of all, what is 3 cubed? That's 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So this is 27. What is 3 squared? 3 squared is 3 times 3. That's 27. 3 times 3, that's 9. What's 9 times 6? 54. It's minus, so this becomes -54. Okay? Look at this. What is 11 times 3? That's 33. So this becomes plus 33 and then minus 6. Okay? What is 27 minus 54? That's -27. Okay? And then I bring down my plus 33 and I bring down my minus 6. What is -27 plus 33? That's actually +6. So I end up with 6 minus 6. What is that? That's 0. So this x value 3 makes this equation true. So I can say here, yes, it is a root, and the associated factor is x minus 3, right? Okay. Now, we could actually continue to try the rest of the possibilities, but we don't have to. Why not? What kind of a polynomial is this? This is a cubic polynomial, or to put it differently, it's a polynomial of degree 3. That means that if it has solutions, it can have of course it can have solutions, it can have complex solutions in the worst case scenario. But in other words, the amount of solutions it can have, unique solutions, is capped at 3. Okay? Here we actually found 3 solutions to this polynomial. The 1, the 2, and the 3. So therefore, we have found all the solutions because we found 3 distinct solutions. That's the maximum we can expect from a third order polynomial. Okay? That's the maximum number of distinct solutions we can have for a third order polynomial. So we can stop here. okay? And what I've shown you here is how we can use the rational roots theorem to make a list of possible rational roots, how we could test them through explicit calculation, how they tell us what the roots are, and what the associated factors is, what the associated factors are, by the factor theorem. Now I want to make a few more, now I want to tell you, or not tell you, I want to show you what I mean when I say that these are the associated factors. Okay, so let's write them down here in summary. Okay, and I'm going to show you what I mean by this. Okay, let me get rid of this table now that we don't need it anymore. Okay. And so let's say I multiply these out. Okay, x minus 1 times x minus 2 times x minus 3. So first I'm going to multiply these two, and I'm going to put the result in this bracket to help us distinguish them, and I'm going to bring my x minus 3 here so I don't forget about it. Okay, so what is the product of these two? Well, first it'll be this x times this x, which gives me x squared, right? This x times that negative 2 is minus 2x. This negative 1 times x is minus x. And then this negative 1 times this negative 2 is plus 2. Then, in the next line, I'm going to simplify this term. Okay, so I'm going to get x squared. What is negative 2x minus x? That's negative 3x, then plus 2, like this. Then I'm going to multiply that times this. Okay. By the way, one of the things I want you to observe here is I keep all my calculations compact and in one piece. I didn't do this multiplication and then at the end multiply this one. I'm trying to keep it all together. Now, it's possible that I may have done this calculation on a separate sheet of paper, right? But I try to keep the logical flow of the calculation that I'm doing together to prevent myself from forgetting some calculation that needs to be done. Okay, so like for example, let me give you an example. A lot of students, what I'll see them do is they'll want to do this, and then in this next line they'll have done this product like this, but they'll have forgotten to bring this down, and so they'll think they're done and they'll give this as the solution, when of course that's not the solution. Okay, so it's just little things that contribute to erroneous solutions, and that damages the confidence of the student, and of course I don't want that. Okay, so by keeping the calculation together like this, it helps to avoid that. Okay, moreover, like as you develop these good habits, you're going to become more and more confident with the calculations. Anyway, let's continue before we go way off topic. I want to multiply these now. Here's how I'm going to do it. I'm going to multiply the x squared times this x, so that'll be x cubed. I'm going to multiply this x squared times this minus 3, negative 3x squared. Notice what I'm doing. I'm going to multiply this times everything in the second parenthesis. Then I'm going to move to this one, and I'm going to multiply this one times everything in that parenthesis, and so on. So negative 3x times x is minus 3x squared. Negative 3x times negative 3 is plus 9x. Okay. Positive 2 times x is plus 2x. And then positive 2 times negative 3 is minus 6. And so now I'm in a position to combine like terms. Okay. Are there any cubic terms besides this one? No, so I can just bring this one down. Okay. There is this square term and this square term, which gives me minus 6x squared. Okay. There's these two x terms. 9x plus 2x is plus 11x, and then there's the minus 6. Aha! Look at this expression. If I multiply these factors out, I get this polynomial, which happens to be this one. Okay? And so that's what I mean by the associated factors. Okay? They are the factors of the polynomial on the left-hand side. Okay? Now, I want to be very clear also. It just so happens that this polynomial matched this one, but that was not strictly necessary. It is possible that this had been some multiple. Okay, if this had been some multiple, if the equation we were solving on the left hand side had a multiple of this polynomial, like let's say each of these numbers had been multiplied by 3. In other words, 3x cubed minus 18x squared plus 33x minus 18 equals 0. Let's say this had been the solution. Let's say this had been the equation we were solving. The rational roots theorem may have given you, well, it would have given you some of the same roots, okay? It would have given you a few more possible rational roots, but it would have given you these roots as well, okay? And you would have gotten that these would have been factors, the associated factors, because you would have seen that for these same values, namely 1, 2, and 3, it would have made this equation 0, okay, as well. And so you would have multiplied those factors out that we would have gotten, and you would have gotten this one, okay? Is there something wrong here? No, because it turns out that this one is just this multiplied by 3, okay? So in other words, I'm making a clear distinction between these being a factor, these being associated factors of the polynomial, just to say that of course, provided you did all the calculations correctly, the fact that these factors are associated to the roots of the polynomial, or in other words, solutions of the equation, will mean that these will in fact divide this polynomial on the left-hand side. Now, whether they will multiply to give you the exact polynomial on the left-hand side, that is what is not guaranteed. But it is the case, for example, that these would have been factors of this polynomial if this had been the equation we were solving, and the only difference would have been that it's off by some constant multiple, okay? So in this case, 3 times that. And if you want to try that as an example, you can do that. Now, I do want to point out just one final thing here, that if we were trying to solve this one, we would have factored out the 3 to begin with, and that would have given us this, okay? But if you had not done that, and you can try it just to see for yourself, you would have gotten the same solutions, namely 1, 2, and 3. You would have gotten the same factors, and if you multiply that out, you would have gotten this result, and you would have seen, aha, this one is 3 times that. And so you could see that this expression on the left-hand side would have factored as 3 times this, okay? Okay, so with that, I hope you've enjoyed this first example, and I look forward to seeing you again soon. Thank you so much.